We can explore alternate possibilities and hypothetical scenarios with ease. Modal logic is not just an abstract mathematical pursuit, it has profound how modal logic is used in fields as diverse as philosophy, computer science, artificial intelligence, and even of reality. At the heart of modal logic lie two fundamental concepts: necessity and possibility. These concepts, often represented by the symbols box and diamond respectively, allow us to express a range of modal statements that go beyond the simple assertion of truth or falsehood. Necessity, denoted by the box symbol, signifies that something is true in all possible worlds. In essence, a necessary truth is one that cannot be otherwise. For example, the statement 2 + 2 = 4 is necessarily true. It holds true in all conceivable worlds, regardless of the laws of physics or the nature of reality. Possibility, on the other hand, is represented by the diamond symbol and indicates that something is true in at least one possible world. It suggests that a statement is not inherently impossible, even if it may not be true in our current reality. Consider the statement, "It is possible that it will rain tomorrow." This statement is true because there exists at least one possible world where the atmospheric conditions align to produce rain. These two fundamental modalities, necessity and possibility, form the cornerstone of modal logic. They allow us to express a wide range of modal statements from the profound to the mundane and provide a framework for reasoning about the nature of truth, knowledge, and belief. To truly appreciate the power and scope of modal logic, it's crucial to understand how it differs from classical logic, the foundational system of reasoning that has dominated Western thought for centuries. Classical logic, with its emphasis on truth values and deductive reasoning, provides a powerful tool for analyzing arguments and determining their validity. It has been the bedrock of logical reasoning, shaping the way we think about truth and argumentation. Classical logic, with its binary approach, focuses on propositions that are either true or false. This binary nature is instrumental in legal reasoning, scientific inquiry, and everyday decision-making, where clear-cut answers are often required. However, it falls short when it comes to capturing the nuances of modality, the realm of possibility, necessity, and contingency. These are aspects of our world that are not easily confined to a binary true-false framework. Classical logic deals primarily with propositions that are either true or false. It provides a robust framework for determining the truth value of compound statements based on the truth values of their components, using logical connectives such as and, or, and not. These logical connectives help in constructing complex arguments and breaking them down into simpler components. Yet this binary framework proves inadequate when dealing with statements that express modality. Consider the statement, "It is possible that it will snow in July." In classical logic, this statement would be either true or false, depending on whether or not it actually snows in July in our current reality. However, this binary approach does not capture the essence of possibility. It fails to account for the fact that while it may not snow in July in our current reality, it is still within the realm of possibility. In classical logic, this statement would be either true or false, depending on whether or not it actually snows in July in our current reality. However, modal logic allows us to express the contingency of this statement, the fact that it is possible but not guaranteed. This is where modal logic diverges from its classical counterpart. It introduces a new dimension to our reasoning, allowing us to consider not just what is, but what could be. Modal logic introduces new operators, such as the box for necessity and the diamond for possibility. These operators enable us to express modal claims and reason about them systematically. The box operator signifies necessity, indicating that a statement must be true in all possible worlds. The diamond operator, on the other hand, signifies possibility, indicating that a statement is true in at least one possible world. These operators expand the expressive power of logic, enabling us to capture the nuances of human language and thought that elude classical logic. They allow us to reason about potentialities and necessities in a structured and systematic way. By incorporating these modal operators, we can better understand and articulate the complexities of our world, from philosophical inquiries to everyday decision-making. Modal logic thus opens up a universe of difference, enriching our understanding of reality and possibility. And knowledge. Kripke semantics navigating possible worlds. While the concept of possible worlds provides a helpful framework for understanding modal logic, we need a way to formally represent and reason about these worlds and the relationships between them. This is crucial because, without a formal structure, our understanding of how different possibilities interact would remain vague and imprecise. This is where Kripke semantics, developed by the philosopher Saul Kripke, comes into play. Kripke's work revolutionized the field by providing a clear and structured way to think about possible worlds and their interconnections. Imagine possible worlds as islands scattered across a vast ocean. Each island represents a different way the world could be, with its own unique set of circumstances and truths. Kripke semantics provides us with a map and a boat, allowing us to navigate between these islands and understand how truth travels across them. This navigation is essential for making sense of how different scenarios relate to one another. This map is called a Kripke model, and it consists of two key components: a set of possible worlds and an accessibility relation. The set of possible worlds represents all the different scenarios we are considering. The accessibility relation determines which worlds are accessible from each other. It tells us which islands we can reach from any given starting point. In essence, it defines which possibilities are relevant when evaluating the truth of a modal statement in a given world. This relevance is crucial for understanding how truths in one world can influence or relate to truths in another. For instance, if we are considering the possibility of it raining tomorrow, the accessible worlds would be those where the meteorological conditions today could plausibly lead to rain tomorrow. This helps us understand the conditions under which certain statements about the future can be true. Crypto-semantics provides a rigorous framework for evaluating the truth of modal statements relative to a given crypto model. This framework ensures that our reasoning about possibilities is both systematic and precise. It allows us to determine whether a statement is necessarily true, true in all accessible worlds, possibly true, true in at least one accessible world, or impossible, true in no accessible world. This categorization is fundamental for understanding the nature of different truths. This framework forms the bedrock of modern modal logic, providing a powerful tool for analyzing and understanding modal reasoning. By using crypto-semantics, we gain a deeper insight into the structure of possibilities and the nature of truth across different scenarios.